Welcome to Dr. Sherry's Astronomy channel. The theme this time is, the first observational evidence of red supergiant evolution beyond our galaxy. The universe is believed to have originated from the Big Bang about 13.8 billion years ago. As it expanded and cooled, it gave rise to various types of celestial objects, forming the universe as we know it today. During the Big Bang, light elements like hydrogen and helium were created, but heavier elements like oxygen, carbon, and iron were not. At some point, stars were formed from just hydrogen and helium. These stars synthesized various elements, leading to the creation of the first galaxies, known as the primordial galaxies. Thus, to understand the evolution and recycling of matter in the universe, studying the life cycles of stars is crucial. Inside stars, nuclear fusion transforms lighter elements into heavier ones. When stars reach the end of their lives and undergo supernova explosions, these heavy elements are dispersed into space. This material gathers as interstellar matter, becoming the raw ingredients for new stars and planets. Dust formed during a star's evolution is also important. This dust consists of cooled and solidified heavy elements and molecules, which are abundant in interstellar space. Such dust can serve as the building blocks of new planets and potentially carry organic molecules necessary for life. The elements that make up our bodies and the materials of Earth were all formed through these stellar processes. Given this, understanding the evolution of massive stars that were abundant in the early universe is essential. Among these, observing the final stages of evolution in massive stars with over 8 times the mass of the Sun, called red supergiants, is especially critical. Red supergiants expand greatly due to nuclear reactions in their cores, causing their surface temperature to drop and making them appear red. These stars are vital for studying the final stages of stellar evolution. The phenomena occurring in this stage hold keys not only to understanding the stars themselves but also to the broader evolution of the universe. Eventually, red supergiants end their lives in supernova explosions. These explosions eject heavy elements like oxygen, carbon, and iron, which were formed in the star's core, into space. The ejected materials contribute to forming new stars and planets, playing a crucial role in the cosmic cycle of matter. Moreover, the immense energy released in supernova explosions not only impacts the surrounding space but also leads to the formation of extreme objects like black holes and neutron stars. Before supernova explosions, red supergiants are thought to undergo intense mass loss, releasing large amounts of gas and dust. By examining the structure and distribution of this dust around red supergiants, we can gain insights into how stars release matter and how this process alters their surroundings. Detailed observations of this phenomenon can also provide clues to the mechanisms and timing of supernova explosions. Capturing structural changes in images is essential for gaining a deeper understanding of stellar evolution. To observe the structures of stars that appear as mere points of light, we need telescopes with extremely high resolution and must focus on nearby celestial objects. One way to achieve high resolution is through a technique called interferometry, which uses multiple telescopes as a single virtual large telescope. This technique is primarily used in radio astronomy, such as with the ALMA telescope. For example, ALMA has been used to observe a red supergiant in the Milky Way, Betelgeuse, which is relatively close to Earth. These observations have revealed details like surface temperature distribution, localized temperature variations called hotspots, and motions that may be the origins of mass loss. In infrared astronomy, the gravity plus optical interferometer is gaining attention. This instrument contributed to confirming the existence of a black hole at the center of the Milky Way by tracking the motion of nearby celestial objects. This achievement was recognized with the Nobel Prize in Physics in 2020. Gravity uses 4 8-meter telescopes as an interferometer to drastically improve spatial resolution, allowing it to capture highly detailed images. The resolution depends on the wavelength of observation and the size of the telescope aperture. Shorter wavelengths or larger apertures result in higher resolution. By combining the light from the four 8-meter telescopes at Chile's Paranal Observatory, gravity achieved a remarkable resolution of 20 microarcseconds using 2-micron infrared light. This resolution is equivalent to distinguishing a golf ball on the Moon, enabling precise monitoring of objects orbiting the galaxy's center. This led to the measurement of the supermassive black hole's mass, 4 million times that of the Sun, and even detected relativistic effects causing orbital distortions. For leading this project, Dr. Reinhard Genzel of the Max Planck Institute for Extraterrestrial Physics received the 2020 Nobel Prize in Physics. Currently, the European Southern Observatory is upgrading gravity in phases under the project Gravity Plus. By enhancing the observation instruments and the 4 telescope facilities, the project aims to further refine resolution. The system corrects atmospheric turbulence, which affects observed images, by upgrading adaptive optics on each telescope. Gravity Plus also enhances fringe tracking capabilities, further improving resolution. This feature uses the interference images of a nearby bright star to monitor and correct for atmospheric turbulence. While radio interferometry uses the target object itself, optical wavelengths require a bright reference star due to differences in light paths. The original gravity required a bright star within 2 arcseconds of the target. However, Gravity Plus extends this range to several tens of arcseconds, broadening the range of observable objects. Recently, a team led by Dr. Keiichi Ohnaka of Universidad Andrés Bello in Chile observed WOG 64, a red supergiant located in the Large Magellanic Cloud, 160,000 light-years away. This star is 2,000 times larger than the Sun. Although expanded images of about 20 stars in the Milky Way have been obtained, Gravity Plus's capabilities have enabled the first ever enlarged image of an extragalactic star. Here's the image. The bright elliptical region in the center represents a dust cocoon surrounding the star. Its long axis measures 13 times, and its short axis 9 times the star's radius. Potential causes for the elliptical shape include bipolar outflows of dust along the ring's axis or an as yet undetected companion star. The faint elliptical ring surrounding it could be the inner edge of a dust ring structure. However, further detailed observations will be necessary to confirm this feature. The research team combined infrared spectral changes with brightness monitoring data to estimate when the dust cocoon formed. For instance, near-infrared spectra have revealed this pattern. The top panel shows measurements from the 2000s, and the bottom shows measurements from the 2020s. Water absorption observed before 2003 had disappeared by 2016, replaced by a smooth, rising continuum. This suggests that changes occurred between 2009 and 2016. Meanwhile, mid-infrared spectra from 2022 match data from before 2007, suggesting the formation of new, hot dust close to the star. By analyzing brightness changes, the team confirmed the estimated timing of the dust formation. Dust dims the star's visible light and brightens its infrared emission. Brightness measurements revealed periodic changes before 2009, but the star dimmed significantly after 2014, supporting the hypothesis of dust formation. They concluded that the dust cocoon began forming between 2009 and 2016, likely in a region about 1.5 times the star's radius. This observation revealed that new dust forms close to red supergiants and affects their surroundings. This discovery is a major step toward understanding the evolution of red supergiants and their transition to supernovae. New dust formation also plays a critical role in galaxy evolution, providing valuable clues to the evolution of the universe. Future observations will aim to confirm whether the outer ring is a real structure, providing even more detailed insights. Thank you for watching, and I'll see you in the next video. If you enjoyed this video, please don't forget to give it a thumbs up. Hit the subscribe button and the notification bell icon, so you'll be notified when new videos are released.